Hello everyone, my name is Samuel Martinez Jr. and this is my Physics Lab 4 for oscillations. A table of contents to give an overview of the lab. An introduction. The purpose of this lab is to analyze a given video of a spring mass system oscillating and using that data create another virtual simulation, and then we can compare the two. I'll be using Tracker and GlowScript for the experiment and simulation. And note, this is option 1. We were given two options, either using a video or performing the experiment in the physics labs. I opted to choose the first option. Some models and principles that will be very important for this. Newton's second law, movement divided by time, F-net. I have a free body diagram there on the right. And the energy principle. So for the sake of this simulation, we're going to assume surroundings are 0. That there's no work from the surroundings, and spring force equation is provided there along with the integral of spring force equation. Here's some brief results showing X seems very similar to itself, but the Y position is a little bit weird. We'll get to that in a bit. Video analysis. The video file is provided here. System, spring, gravity, and mass, with the surrounding not being anything. Initial conditions are that velocity is 0 and the position is marked. That's given using the tracker data. Some of our beginning characteristics are also given by a video. Video 52 from the week 8 previews is what I was told to reference. So the calibration length is 0.7 meters. The video frames per second is 10.53. We're sticking with deltat 1 over 210 that was provided in the GlowScript code, and it should work for our purposes. Mass 4.402 kilograms, spring stiffness of 6.83, and a relaxed length of 0.213 meters. Some video analysis. Those numbers were provided in the video already, but here's just showing how to figure out spring stiffness using a period of oscillation being from one complete cycle of the spring. So you take 3 cycles, divide that by 3, gives you t time, which is period of oscillation, and the equation for that is 2 pi with the square root of m over k, and manipulating the formula allows you to find k, which is approximately 6.83. This is the tracker application opened up here. The X and Y columns, we took the data from Tracker, put it into Excel, turned that to a CSV file to feed that to the GlowScript simulation. Just to look closer at that, L0, the spring stiffness, gravity, and kinetic energy, as well as change in gravity and change in spring force. Further calculations to update. This, if you will recognize, is the position update formula, as well as the velocity update formula. And some of our results. The ending graph ended up being where we have a straight curve almost for change in energy. Although it's not a perfect line, this does go along with the energy principle, being that there should be no change in the total energy of the system. There are little burps and hiccups along our graph, and I'll get to that point in a bit. So for the X position versus time, the model and both the experiment both followed about the same curve. They were slightly off, probably due to just a timing error. But the Y positions did have a larger disparity between the two of them. The only possible errors I can think of are that the calibration stick may not be super accurate to what the video shows, or that the video actor who lets go of the weight is adding in another force, probably moving along that weight on the z-axis. The weight might also bump into the back plate and change its trajectory. Also, this is probably not a perfect oscillating shape if it did bounce off of the back wall. So, for the model system, is the energy principle satisfied? I believe yes. For an energy system, if we assume that the surroundings do not affect the system, which they do not for this experiment, there should be no change in the energy of the system. That orange line in the graph represents delta E, and although it varies a little, it can be assumed that there is no change in the system. These are the two periods of oscillation calculated for X and Y direction, and they are different. This would affect how wide of an arc there could be made in each direction. And this also may be an added reason to why we may have errors in our graph. Thank you very much for watching.